And good morning, friends. We are into our, second week of relativity, having started last week. So we're going to continue this and work on a couple of more topics to do with special relativity. And then I think we'll be done with that. I'm not sure today, maybe today or tomorrow. And we'll go from there. So just by way of reminder, PLC 12 is on special relativity. Now, as of right now, I have not yet posted that because I was out yesterday. So I will be posting that later today by the time this video gets put up. So hopefully that'll be okay. And then the homework, which I had said originally was going to be Thursday of this week, I think that we are running a little bit further along in the topics than I had initially anticipated. So I'm going to push that back to Tuesday, which is a week from right now, at least. So I'm going to push that to Tuesday of next week, which means that's going to be the 6th. I think. Is that the 6th? Yeah. Because I think we just need a little bit extra time. And who doesn't need a little bit extra time? So let's, there will on that day be the quiz that is associated with the homeworks at the same time. So that will be plus quiz at that point. Okay. So to keep going with where we left off, I believe we left off with the idea that time could be calculated in different frames via a what's called dilation formula. So I went through an example last time of a train and a light clock on the train, and we were looking at the different paths that light took. If we were on the train, it would go up and down. If we were on the station platform, then it took a much longer kind of hypotenuse triangular sort of thing. And the end result of that is that the time between clicks, as observed by an observer on the station platform, they are observing the train on the clock. So according to that observer, the train on the clock is ticking slower. This is known as dilation because dilation, if you've ever gone to, for example, not the orthodontist, the optometrist, the one that does the eyes, and they put the drops in your eyes that dilates your pupils, that makes them bigger. Well, that's what the dilation is referring to. It's referring to the time between clicks getting bigger. Hence, time runs slower. Okay, so that's dilation of the time. But it's important to remember, I'm putting clicks or ticks of the clock or whatever it is that is making the repetitive timekeeping motion. So the time between clicks gets larger on the train clock as observed by someone not on the train. As observed by what I use the station platform. Someone station platform. Like so. Therefore, the time as observed by that observer is slower on the train. However, according to a train observer, and this is where you have to really make sure you draw a good distinction, the time on the train as observed by a train observer is exactly the same as it always was. Our personal time is in our personal reference frame. So as we are in motion or we observe others in motion, it's always someone else's clock that's running slower than ours because that clock is in motion, okay? So what it depends on is the idea of the clock moving clocks running slower. And that's the idea of time dilation. The Earth observer looks on the train clock and sees the train clock ticking slower than the Earth clock. Now, the person on the train does the exact same thing, looks at the Earth clock, because on the train what you're doing is you're watching the Earth clock zoom past this way, and you're doing the exact same thing. You're looking at my light clock, and I'm looking at that light clock, and I'm saying your light clock's running slower than my light clock. So there is a paradox here. Because when this first got discovered, when Einstein first came out with the relativity theory, people started saying, okay, but which one's true? Which perspective is the right perspective? Now, we might look back at that and say, ah ha ha, that's such a silly question. There is no universal frame. But think of it this way. Special relativity in 1905 was now questioning the foundations of science that had been put down by Newton in the 1670s. All right, so you're talking about what, 230 some odd years worth of people going through thinking there is an absolute space and an absolute time. Everyone measures the same time. I mean, it was even before that, if you want to think about Galileo, who was in the 1500s, right? You're talking about hundreds and hundreds of years of thinking, and then not getting any evidence that the thinking is in any way incorrect. So Einstein coming along and saying, well, what about this? Of course, people said, well, that's ridiculous. Everybody knows the time is the same. Well, when this type of thinking came out and the clocks are running slow, you'd say, well, your clock's running slow from my perspective, but my clock's running slow from your perspective, so who's right? Okay? And this is the basis behind the thing that we left off talking about, which was the idea of a trip, a spaceship trip out and back, in which there are different times measured. Now, the question of well, who's right comes in when you look at this idea of a journey out and back on a spaceship. Suppose the spaceship is here on Earth, it blasts off, or suppose that the person jumps onto a fast-moving spaceship that doesn't have to accelerate, so we don't have to worry about that type of thing, and it turns around and comes back. So at all points, the person on Earth would look at the spaceship clock and say, that clock's running slow. And then at all points, the rocket ship person would look and say, my clock is normal, Earth is moving away from me, Earth's clock is running slow. And that's what became known as the twin paradox. In other words, imagine that you had two people born at exactly the same time here on Earth, and one of them, after, 25 years, say, or something, jumps onto a spaceship and blasts off and goes away and comes back. And by spaceship time, it only took, say, 10 years. But on Earth time, maybe it took 40 years. So how can it be that if each person, each twin, looks at the other's clock and says, your clock is running slower than mine, how can it be that one twin definitely ages less than the other one? And this is what the paradox is. Now, I will preface this, since we've kind of already gone through a lot of this, I will preface this with the following statement, which is that there are many paradoxes that are brought up in special relativity. They are all paradoxes in which they were presented as a way to either say, this can't be right, or we don't understand what's happening here. All of the paradoxes have basically been solved. So they aren't paradoxes from the special relativity viewpoint. Now, there is one caveat to this, and it happens still to this day, which is that, please remember, all of this special relativity can be completely disproven if you ignore one thing, and that thing is the simultaneity of events. So if you forget that simultaneity of events is no longer preserved between different frames of reference, then you can completely, you can show that special relativity is completely wrong. However, SR tells you that that simultaneity should not be preserved between different frames, and therefore it should be okay. So every paradox has a resolution in SR. Now, the twin paradox is the one in which we kind of talked about this last time. It's the one in which someone blasts off, looks back at clocks, and we look at their journey, they look at our journey, and then we make comparisons. Now, what I did was last time I showed you that the journey as, let's see, I'll just draw my 45-degree line here. Okay, so this is my c equals 1 line. So the journey perhaps took something like this, we'll say to there, and maybe something like that. That's not quite right, but that's okay. So this would be the x prime and the t prime axes. And then on the way back, what they do is they turn around, they come back. So then this point here goes to that point there, and this becomes the t double prime axis. And then the x double prime axis would look like, it's going to look like that. X double prime. Something like that. What I'm doing here is I'm sketching out the axes of the rocket ships as they travel away from Earth and then back towards Earth. The away from Earth situation, we already have pretty much figured that out in the sense that around the c equals 1 line, they are symmetric. So they go the exact same angle inwards. From here, they go in by the same angle. Well, the same is true on the journey back. The axes splay outwards by the same angle, and thus speed of light is preserved for both cases. So what has happened here is that if you look at the c equals 1 line, then these two axes have gone away by the same amount. So the x double prime axis is that way, but think of it as think of it in the same way as we were thinking about the x and the x prime axes. In other words, it still tells you the simultaneity line, okay? So if I follow this line here, I'm going to say, well, look, there's simultaneous with the rocket ship leaving the planet, Earth clock is reading this much. Simultaneous with the rocket ship arriving at the planet, that would be along the x prime axis, that would be this way. Something about like that. That's the clock reading on Earth when the rocket ship arrives at the planet. So that's the arrival time, that's the rocket ship arrival at the planet. This is Earth clock at the point when the rocket ship departs the planet. So this is according to the rocket ship time. I'm sorry, not time. This is the time on Earth according to someone on the rocket ship. And so what happens is, from the Earth perspective, we look out there and see them zooming away, and their clock is running slow. So our clock here on the rocket ship would be reading, I think I would use something like 1 week or something like that, or 1 year. So our clock is reading 1 year, but Earth clock, when we arrive at the planet, this is Earth time. This is Earth time as seen by an Earth observer at arrival and departure. That's seen by an Earth observer. And maybe that's 3 years. Okay? So Earth looks at Earth time and says 3 years. Earth looks at rocket ship time and sees 1 year. Therefore, Earth says, your clock's running slower. Rocket ship person says, zoom, my clock reads 1 year, okay, when I arrive at the planet. And I'm getting a notice that my internet connection is unstable, which is not a happy thing. Huh. Well, hopefully everything's going okay. Rocket observer says my clock reads 1 year. I'm going to look back and see what Earth's clock's reading. So simultaneous with that, that's Earth clock as seen by the rocket ship. So this is the, say, 1/3 of a year mark. Okay? So that would be 1/3 of a year. If that's 1 year and this is 3 years, then this would be 1/3 of a year. Then this would be 3 years. And then this, now the rocket ship is about to leave the planet and it looks back at Earth's clock and says, or it looks forwards at Earth's clock maybe and say, okay, what is this now? Well, it's going to take, according to Earth, it's going to take 3 years for this person to come home, which means this is now reading 5 2/3 years. Because according to the rocket ship, Earth is on its way back to join me, and it's only going to take 1/3 of a year, whereas by my clock, it's going to take 1 year. So the viewpoints are preserved in the sense that I look at your clock and I say, your clock's running slow. You look at my clock and say, my clock's running slow, right? So it's all true, but there's an asymmetry that happens, and it's right here at this corner. Okay? It's right here where the rocket ship eventually turns around, or the person changes reference frames. That's an event, and that's an event that everyone can agree on. Everybody says, you changed frames, so it's your clock that is kind of doing the round trip motion here. You're going out and coming back. And therefore, during the time of the rocket ship arriving and then departing, Earth's clock swings from here to there. We see all of the Earth's kind of quote-unquote past happening in a quick burst, and then we go on about our business and watch their clocks running slow as we don't approach anybody, as Earth approaches us from the rocket ship perspective. Therefore, there is no paradox in the twin paradox. The twin paradox is, yes, indeed, somebody comes back less old than the other person. And we can tell because the rocket ship was definitely the one that accelerated. And yes, this is really what would happen. If you're interested, this has been experimentally tested. Now, I will say the following. If you're interested in looking at the experimental test, it's by Hafele and Keating. So what they did was they took an airplane, I think they took a Navy plane, and they took an atomic clock, which is super precise in terms of its timekeeping, and they stuck the clock on the plane, and they put an exact copy of that clock on the ground, They synchronize the clocks, right? So they're ticking exactly at the same rate. They read the exact same time. They put one of those clocks on the plane, they fly it around. All they did was they flew it around in a circle for like, I think it was almost 24 hours in a row or something like that. They had a couple of pilots on the plane. It was something like that. They did something, I can't quite remember the amount of time they did it. This was back in the 70s? I think it was back in the 70s, maybe early 80s. And they just flew the plane around. I think it was it was near Bethesda in Maryland. They did it right over there, and they just went around in a circle. And then they stopped, took the clocks off. Sure enough, they're different. Now, there are a couple of things that are at work here. One of them is a special relativistic viewpoint in which that clock is in motion with respect to us at all times. And therefore, it will run slower as observed by us. However, that clock, if you were going around in a circle, that clock is accelerating the entire time, which means there's also a general relativistic time dilation that happens due to the acceleration. However, if you calculate both of those things, it turns out that the clock agrees with what it should be off by. So it's both a GR situation and an SR situation. They did the calculations and the clocks, and they looked at what the clocks read, and their calculations matched what the clocks told them. So Einstein, as far as we can tell, is actually still giving us the right answers. Now, let's talk a little bit about some other experimental verifications of SR. There are a couple of other things that happen because of special relativity. I just had one in my head and I just forgot what I was going to say. Let's do this one. Let's talk about the light beam. So people in Harvard shot a laser up a big, large tower. They have a big tower, and they have a tunnel, like a basement underneath it. So what they did was they shot a laser straight upwards. This is not really a special relativistic thing in the sense that, well, it is kind of. So what they did was they looked at the frequency, and they found that as the light is ascending, the frequency is changing. Okay, it's actually lowering its frequency as it goes up. Now that's also a GR situation, but it also is a bit of a Doppler effect. Einstein had to also, as part of special relativity, correct the Doppler shift. The Doppler shift, as given by the classical viewpoint, says that it depends on the speed of the observer with respect to the speed of the source and the speed of the waves. And Einstein had to correct that, because if you knew that you're moving with respect to the with respect to the source, if the source is moving, you get one answer. If you're moving, you get a different answer, and that means you know how to tell the difference. And Einstein had to change that and say, no, it's just relative motion between the two, in which you get a Doppler shift. So that happens, and then, gosh darn it. Okay, I'm gonna have to move on, because I had something I wanted to say, but I forgot what it was. So we're moving on. I will probably stop and come back to it later. It had something to do with that. Anyways, okay. I want to go talk a little bit about simultaneity, and remind you that the times. So the time in a reference frame, which I usually called S, time in the S reference frame is equal to gamma times the time in the S prime frame. That's the time dilation kind of quote unquote equation. And one thing to remember is that the S and S prime frames change. Now, you're saying, wait a sec, that can't be right. No, it's okay. It just depends on who's looking where, okay? The S frame is not always the Earth frame, okay? The S prime frame is not always the moving frame. So in the way that I've put it out here, really what I want to say is that this time here should be the proper time. And I talked a little bit about the proper time, last class, but the proper time is the one in which there is no motion of the clock relative to an observer. In other words, if I look at the clock and I'm on the rocket ship, right, as I'm leaving, well, I don't leave, Earth leaves me, right? So as Earth blasts off and goes back that way, I look at my watch and I go, look, my clock is telling the time in my reference frame, and it's not moving with respect to me, but I see Earth's clock moving that way, so it's in motion with respect to me. All right? So to get the proper time, so say the proper time in the case of going from Earth to the planet, to this planet where the rocket ship lands. The proper time getting from Earth to the planet is given by the rocket ship. Because the rocket ship looked at their watch and said, my watch is not moving. My watch is not moving. My watch is not moving. La, 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 la. Here comes a planet. We're going to stop. Okay. And the entire time, my watch was right there. So the time on the T prime axis is the proper time. And therefore, the time in the Earth frame would be given by gamma multiplied by that number. And that's why the Earth time ends up as being 3 years. Likewise, if I flip it around the other way, and I say, I'm looking back and saying that Earth is, or the people on Earth are looking at their watches saying, my watch is not moving. Therefore, what's going on with your watch, right? Well, this doesn't really work so well, does it? Because I got to really think about what's seen by the rocket ship. Never mind that. Okay, we're going to move on. The proper time, I just want to put this into definitional form. So this is the proper time. This is the time as given by a clock that is not in motion with respect to the observer. Now, typically, we can agree on who has the proper time. So, this is kind of the point I was going to try and make. But if I'm on Earth and I'm watching the clock on the rocket ship leaving, I can see that the person on that rocket ship and the clock on that rocket ship do not move with respect to one another. Right? And so I would say, well, the rocket ship just took the clock from Earth all the way to that other planet. And that clock moved with respect to me. All right? So I can't be measuring the proper time. Right? The person who's on the rocket ship would have to be measuring the proper time. And therefore, the time on my watch is going to be larger than the time on their watch. Okay. Let's do this then. Let's talk about speeds. So if we have a speed, typically what we would do for a speed, and remember this is special relativity, which means we're talking about things that are moving at constant speed. We would typically think of a speed as a distance over time. There's no accelerated motion that we're talking about here because we're talking about constant speed, constant velocity motion. So we only have to worry about distance over time for speed. But the problem is that we're going to have an issue with the time. Okay? So if we're going to agree on a speed, like, for example, we have to agree on light speed, right? And typically, if someone's moving this way and someone else is moving that way, we're going to agree that we're moving at the same speed no matter which frame we're in, because it has to be symmetric between the two observers. There's not a situation in which I would measure you going at 0.5 that way, and then if I jumped onto this frame, I jumped onto your frame, and I looked at my old frame, and I say, oh, my frame's moving at 0.8 that way. There's not a situation where this happens. If I look at your frame and I measure you going at 0.5, then I jump to your frame and I look at mine. Mine's going the other way at 0.5. Okay? So we have to agree on these speeds. The problem is that we don't agree on times now. So if I'm going to agree on a speed, then I look and say, but we disagree on how much time happened. The problem here is we are now also going to disagree on how much distance was covered. Okay? So there's disagreement here. Different observers will disagree on the times. And therefore, as a consequence of that, we have to also disagree on the distances and the positions of things. Okay. So if I think of the distance, now I have to think about, if I'm going to measure something, and I'm going to say I want to know what the speed of something is, I have to use one frame. So that means I have to take the distance in one frame and divide by the time in that same frame, because if I do distance in one frame and time in another frame, that's not a thing. Okay? So we have to make sure they're in the same frame. So I need to say that I need a distance, for example, in the S frame, and I need a time in the S frame. All right? And I'm going to say that's going to equal a distance in the S prime frame, but not the same distance as I measured, but it will be the same ratio if I divide by the time in the S prime frame. Okay, as long as I keep these consistent, right? These are consistent, and I don't start mixing distance in S divided by time in S prime. No, that's not a thing, okay? Then I can say these two quantities should be equal because we're going to agree on the speeds. For example, we have to agree on light speed, okay? So the time in S, you can see, is gamma multiplied by the time in S prime. So if I take time in S, I could say this is equal to gamma multiplied by time in S prime. So this tells me how I have to be able to measure the distance in the S prime, in the S frame, and the S prime frame. This has to be, distance in the S has to be equal to gamma times distance in the prime frame. Because if I'm dividing by gamma, and I need this to still be the same number as, I need that to be the same number as this, then I need to get the gamma out of there. Okay? So this gives us a little bit of a clue as to how the distances are related. Okay? So, I don't really want to erase this, but I'm going to have to. So, what this tells us then is that the distance as measured by someone in the S prime frame is equal to the distance as measured by someone in the S frame divided by the gamma factor. Okay. Now, I want to put this into context, so let's talk about what's happening here. Remember that the gamma factor, gamma is always, well, greater than or equal to 1. There's basically no point in it being equal to 1, and we're not really talking about relativity. So gamma is always a number that's bigger than 1. As V gets higher and higher towards 1, then gamma gets higher and higher towards large numbers, infinity and stuff. So what this means is that this distance is a shorter distance than this distance is. Okay? And therefore, if I'm going to say that this time is a longer time here, right? What I did was I just kind of switched it around by dividing by the gamma, but that means this distance has to be a longer distance. It's gamma multiplying the distance in S prime. So the gamma is a number that's greater than 1 in order to tell us that the time is greater, but now this is telling us that the distance is also greater. Typically, the way this is thought of, though, is as a shortening. This is known as the length contraction. And what this means is that if there's something in motion with respect to you, then you're going to measure it as being a shorter object along the distance of its travel. Okay? they appear to be contracted. In other words, they are shortened along the distance of their travel. I shouldn't say distance, I should say along the direction of their travel. Okay. So we'll go back to the space-time diagram that I just erased, the twin paradox one. Now let's look at it from both perspectives. Let me get rid of this. Here's what it looks like from Earth's perspective. Okay, here's Earth, and here's a planet out here. Okay, this is planet P, this is Earth E. And what we see as observers on Earth is a rocket ship leaving here right? The rocket ship leaves here and goes and arrives here. What we do on Earth is we measure there's a distance between us and this planet because more or less this planet's probably at rest with respect to us, or at least reasonably so. In other words, it's probably not traveling at 0.8c with respect to us. It's probably traveling at not much of a speed, so we'll call it in the same reference frame. Now, the rocket ship is traveling at some speed, which is significant compared to light speed, because that's what we're talking about. And we here on Earth measure a distance between us and the planet, which is the distance the rocket would have traveled according to us. And we measure a time on our watch. Okay, I'm going to say, all right, the rocket ship left here, off it goes. I'm going to time on my watch, and as soon as it arrives on planet P, I'm going to stop my stopwatch, I'm going to look at the time, I'm going to take the distance L, I'm going to divide by the time, and I know what the speed of the rocket is. Okay? No problems, right? Well, if I'm on the rocket, I'm going to look at my watch, I'm going to look at Earth, taking off going that way, right? And I'm going to watch planet P coming at me this way. Because remember, I'm on the rocket ship now, so from my perspective, I'm not moving. Earth blasts off that way, planet P is approaching me this way. I'm looking at my watch, and I'm going, okay, here comes planet P. I'm going to stop my watch when planet P is nearby. Okay, boom, here comes planet P arrives, I stop my watch. Now that time is not the same as the Earth time. We've already established that, right? That's dilated. But what has the rocket traveler measured? The rocket traveler has measured a shorter time. So if the rocket traveler measured a shorter time, they must also have measured a shorter distance, because the V has to be the same number. And they're not measuring V for themselves, they're measuring V of the planets going this way, right? Just as we on the planets are measuring the speed of the rocket that way, the speed of the, when you jump to the rocket frame, the rocket is measuring the speed of the planets going this way. So, the rocket ship measures a shorter time, therefore it must have measured a shorter distance, and that's what this length contraction is talking about. From the perspective of the rocket ship, the distance between the two planets is shorter because it took less time for me to get there. And that's why the rocket ship person says, yeah, I arrived there in such a short amount of time because it wasn't that much of a distance to travel. Right? So that's how the agreement can kind of take place. The length of the distance between the planets is contracted as seen from someone on the rocket ship. Okay? Why? Because according to someone on the rocket ship, this distance is going that way. And that's why you would measure, I'm standing here in my reference frame and I'm measuring that distance and it's moving past me and it's shorter because it's moved past me. Okay, now, here we are in the Earth frame, and we're saying, okay, here's the distance. Let's see, I can't, just barely fits it on the, oh, this is a good problem. I just barely fit it. Here is the distance from Earth to the planet. Let's put it back a little bit. Okay, here's distance from Earth to the planet. You can measure this. This is just whatever distance it is from here to whatever distance it is from here. Happens to be that this is a 2-meter stick, okay? Now, if we're in motion though, right? If it's in motion with respect to us, this is as measured from Earth now. I'd see this much distance between Earth and planet. But now if I'm on the rocket ship, that distance is in motion with respect to me, which means as it goes flying by, do you see how it shortened? Yeah, see, it's the same stick. I'm just picking up the same stick and I'm just having it, it just happens to go faster. And I mean, when it goes faster, it happens to be shorter. So it's like this big. Right? But if I come off and I'm going to throw it that way, then it's going to, and there it goes. So it was definitely shorter. That's what it means when it says distance in S prime, distance in S and gamma. So here, the distance in the rocket frame, in this case is the rocket frame, is the distance as measured by the Earth observers divided by gamma. So the rocket measures a shorter distance. Which makes sense because they measured a shorter time. However, the notation of proper is now different. Now the rocket ship measured proper time because remember that rocket ship watch did not move with respect to the rocket ship observer. In this case, since the planets are not moving with respect to one another, therefore the people who measure the proper length are the Earth observers. That means this quantity right here is the proper length. The proper length is measured by people for whom the distance is basically at rest. Just as the same way you measure the proper time with the person whose watch is at rest, this is measured by people whose distance is at rest. Oops, at rest, with respect to, oh man, this pen can't spell. Let's try that again. With respect to, there we go. So the observer is at rest with respect to distance L. In other words, the rocket ship cannot be measuring distance L because that distance is moving past the rocket ship. So to put this into perspective, let me tell you one other thing. And that is that if you have a stick like this that's moving with respect to you, the length of the stick is not short, the length of the stick is not shorter. Right? So if the stick is moving like so, what you will see is this. Okay? It has this thickness, but when it's in motion with respect to you, it has this thickness. It's not going to be changed top to bottom. If it was moving this way, then it would be, right? As if it's moving this way, then you will find that the length shortens. But it's only the dimension that is along the direction of travel that is contracted. So in this case, if this is a meter stick, which it is, then it still measures 1 meter top to bottom as it moves, but its length shortens. Its thickness shortens. That's what I'm saying. Okay. All right. Okay. So let's take a look at this. I want to set up a situation here. Once again, we're going to go to a train. here's a train and it's on the tracks. Now I'm going to draw several snapshots of this below hand here. So I'm going to leave a lot of room below in order to do that. And hopefully this will be just fine. All right, what we have here is a person standing halfway between the two ends of the train. Say 1/2 of D to there and 1/2 D to there. All right. Now, at that same position, in other words, directly right here, is another person standing there, and they're lined up. Okay, so these two observers are lined up. And the train is moving, as usual, left to right. Right when these two observers are lined up, lightning strikes. This is pretty cool lightning, because what happens is directly below the end of the car, lightning strikes right there. But simultaneous with that, lightning strikes this end of the right of the track, right under the car. And the lightning leaves char marks on the train tracks. Okay, lightning leaves char marks on the train tracks. So the marks, the char marks are burned onto the railroad tracks. Okay, once again, this is an event. These mark events because physical things have happened that everyone has to agree on. Okay, I mean, you can't switch to a different reference frame and go, oh, there's no char mark. No. There's a char mark. We're just going to disagree on when and where it happened. Now, the train's in motion with respect to the observer here on Earth. Okay, the observer on Earth sees both, or let me put it this way: the light from the lightning strikes reaches the observer on Earth at the same time. In other words, this person is halfway between the two lightning strikes. Light is emitted, chars the tracks, and that light travels this way and then hits the observer at the same time. All right, so this observer, light arrives at the observer simultaneously. Okay. And hopefully you can see why that is. Now, even as the train moves this way, the light is going to have been detached from the train. It's not going to care what the train's doing. The light is going to have struck these 2 points, which are equidistant from this person. Since light travels at light speed, then light will cover those 2 distances, which are equal, in equal times, and therefore they will arrive at this person simultaneously. Okay, now, question being, what does it look like from the train observer's perspective? Incidentally, the person who is here on Earth says, by the way, these two, since I'm halfway between the 2 lightning strikes, and they happen simultaneously, I can measure the length of the train, right? I can measure the length of the train because these 2 lightning strikes happened simultaneously, and I was equidistant between them, and they arrived at me simultaneously. So I can measure the length of the train. All I got to do is measure between the 2 char marks, right? So suppose this person is also interested in making a measurement of the train length, the train car length. Let's see what it looks like from the perspective of someone on the train, okay? Now, the train is moving left to right. question is, there's a difference in what is simultaneous, okay? The Earth observer says the lightning strikes were simultaneous because the light from the two simultaneous lightning strikes arrived at me simultaneously. We have to be able to distinguish between these two simultaneous events, the two simultaneousnesses of them. They're different, okay, in the sense that, how? Okay, let's look at it. Is there a way for us to arrange for an event to be signaled to everybody? So that, is there a way for us to say everyone agrees on the simultaneity of the light arriving at this observer? Is that a thing that we should agree on? Because remember, special relativity should tell us that we disagree on times and distances, not that we do agree on them. But the question of this simultaneous, is that a thing that we can make into something that everyone agrees on? In this case, the answer is yes, but it's a different kind of simultaneous than the lightning strikes being simultaneous. Here's why. Suppose I have two light detectors, okay? I'm going to face one this way, I'm going to face one this way. And I'm going to wire them up such that if light hits this one, but doesn't hit this one, nothing happens. If light hits this one and doesn't hit this one, nothing happens. However, if light gets into this one at the same time light gets into this one, I'm going to have it raise a little red flag or shoot a little balloon in the air, okay? So that when I put that device where this person is standing and the light from this lightning strike arrives from that side and the light from this lightning strike arrives from this side, if they're simultaneous, then a flag goes up or a balloon gets launched. What's going to be fun? Like a little smoke cloud, puff of smoke, whatever it is, okay? But that means everyone's going to have to agree that that thing happens. The flag does go up. There's not a reference frame in which you can say, no, the flag didn't go up. If the flag goes up, everybody sees the flag go up, okay? So that means I can arrange this simultaneousness to be an event that everyone agrees on, all right? This is something that everyone agrees on. Let's just say everyone. Everyone agrees that this event happens. Everyone agrees on this event. Because I've been able to define it as an event. Okay. Now, let's look at the simultaneity of these lightning strikes. Are these events? Yes, they are. But they're separate events. The light hitting here and hitting here from both sides simultaneously is a single event. These are individual events. So notice the difference. When I say light arrives at this person simultaneously, that means that's one event. It involved multiple things, but it's a single event. The thing about this happening over here is that that's its own event. This happening over here is its own event. These events do not necessarily have to happen simultaneously. However, they did for the Earth observer in this case. Let's look at what it looks like from the train observer before we run out of time. Okay, all right, let's see what we get here. What's going to happen here from the train perspective? From the train perspective, the Earth observer is moving this way at speed v, okay? And what we are going to agree on is light hits that person at the same time. Light from both strikes hits that person at the same time. All right, so let's look at it from the perspective of the train observer. Actually, you know what? Let's do this. I'm going to draw it over here and give myself a little more room. Oh, I'm also going to leave a note here that this person also measures the length. Okay, so I'm measuring the length of the train via measuring the two char marks from simultaneous lightning strikes, okay? Looks like a totally valid measurement. Let's take a look at this again from the perspective of the train observer. And what that means is we're going to draw it this way, like that. And whoops, wait a minute. Where's the middle of this thing? Here, right there. Okay, so let's start a little bit before. So my Earth observer, say, is going to eventually arrive there, but right now is over here. Okay, so they're going like this. Okay, here's what it looks like from the train car observer. And hopefully it makes sense how I described it from the Earth observer's perspective. Here's what it looks like from the train car observer. The train car observer notices the person moving right to left, starting over here, and is going this way. Yeah, it's going this way. So, according to the person on the train, if light is to be received by that observer simultaneously from both lightning strikes, we have to see one of these lightning strikes before the other one. Here's the reason why. I'm going to say, at this point, lightning strikes here. This is the number 1, say. Why does lightning strike there first? Notice what has to happen. This person is going to arrive at this dashed line, and light is going to arrive from both sides of that dashed line at exactly the same time, because the flag goes up. Everybody agrees. So when this person's going towards the dashed line, they're going to take some time to get there, but light's also got to go and get there at the same time they get there, right? So as they're moving past, I should probably move this person in a little bit because it looks like they're going to go the same speed and distance as light. So let's do this. Person's here, moving that way, all right? So the person's here, and they have to go 1, 2, 3 squares, but light has to go 1, 2, 3, 4 squares, okay? Light is going to have to kind of catch up to this person. So its relative speed, according to the person on the train, is c minus v. That means when this person then arrives at number 2, at square number 2, okay, then the second one's going to go off because the person's going to go towards the middle of the train. But what's happening then is this light from this lightning strike has to catch up to the person. But the person's going towards this one, which means that light from that from that strike is going to run into this person quicker. Okay? So they go here, this one goes off. It starts to catch up to the person. Okay? I'm going to have to draw this in several different ways, all right? Let's go here. Let's go here now. Like that. So they've moved 1 square, which means light has to have moved 1 1/3 squares. So this light is now, say, here. Light from light number 1 is now here. It's going that way at C. At this point, this lightning strike happens and chars this place. This is number 2. It goes off a little bit later. Okay. As the person moves a little bit closer, it's gone 1 1/3. The person's still going this way. Okay. The light from this one is now catching up. It's going 1. It's got to go 1 1/3. So it's like here. It's about to catch the person, and this one's not going to look quite as right. But the problem with this is, right, you got to think about the perspective of the train moving, or the Earth moving under the train. So you're looking at it as though you're over here, right? and the light has to chase you down to catch up to you, but the light from this side is just going to arrive straight at your face really quickly, right? Now, I know that they're both doing C, okay? It's just not going to really be great from this diagram. So number 2 happens, and then light from here is going this distance to here, which means it's not quite going to manage. So we're probably, say, here, and it's moving that way. And then by the time this person gets to here, right, this light beam has reached from this side, this light beam is reaching from this side, and they say, it's simultaneous. Okay. Notice though that this light had to chase the person in order to catch them. Okay. And that's why, according to someone on the train, lightning strike number 1 had to go off first. Lightning strike number 2 had to go off second in order for the ending result to be simultaneous hitting of the person from both sides. Okay? So my diagram is not doing a great job here. I should probably tweak it a little bit to figure this out. But the point being here that because the person on the train is watching the person going this way, and then there's the agreement that light is going to hit this person simultaneously, right? So what's happening here is the person's going, light's coming this way to chase, light doesn't have to spend quite as much time coming this way, and then everybody arrives at the center, okay? Therefore, lightning strike number 1 went off first, lightning strike number 2 went off second. That's according to the person on the train, okay? Which means that if you now look at the char marks, and once again, you have to you can't quite see this here, but if you look at the char marks, then what you're going to notice is the person on the train is watching the Earth observer and Earth go this way. Yeah, it's going this way, right to left. Which means that if char mark number 1 happened first, before char mark number 2 happened, then char mark number 1 also moved because the person on the ground is moving, the person on the ground is moving past, but all of Earth is moving past at the same speed. Right? So if you're on a train and you see a tree go by, and you look down and you see a railroad tie next to the tree, they're both going to move past at the same speed. It's not like the tree's going to move this way and the railroad tie is going to stay here. So when this goes off first, that char mark moves this way. Char mark number 2 then happens, and that causes this person to say, you are not measuring the proper length of my train. Even though it looked like they did from this perspective. Right here, the person would say, yeah, look, the char marks were occurring simultaneously. I was halfway between, and therefore the light hit me at the same time, which means that these had to have happened simultaneously at both ends of your train, so I should be able to measure the length of your train. But the person on the train is saying, no, that lightning strike went off first, you moved, and then this one went off, which means you're measuring a shortened version of my train. And that's what the length contraction is. If you measure the distance between the char marks, then according to the person on the train, you have not measured the correct length of the train. That is not equal to length of train. So how do we get around that? We get around that by saying, according to this person from this perspective, the train was shortened. When you say that, then you'll say, oh, now I see why this person is saying you measured a shortened length of the train, because the two measurements happen not simultaneously for that person. even though we measured them simultaneously here, the entire length of the train was less. So really, according to this person, the train length was actually this big. According to this person on the train length is actually like this big, right? So we're actually, as Earth observers, we're measuring a contracted length. And therefore, this person is trying to alert us, hey, you're measuring a contracted length. How does that person know that? Because they're at rest with respect to the train, which means they are measuring the proper length of the train. And therefore, we are measuring a contracted length of the train because we're not in their reference frame. Okay, so that's a little bit on the length contraction. I just wanted to give that a bit of historical perspective here. Let's do this and do a quick example of running through a few things. I'll do this first and then we'll end on a bit of historical perspective. Here's a quick example of calculating a length contracted event, or I'm sorry, a length contracted distance. Suppose there's a rocket ship. Okay, the length of the rocket ship as measured by the person on the rocket is 130 meters. Okay, rocket ship length is 130 meters. So person on the rocket says, oh yeah, right? I measure the length because I'm on the rocket ship. I take my tape measure from one end all the way to the other end, and I measure the entire length of the rocket ship. Okay. What does it look like to us here on Earth as the rocket ship goes zooming past at some horrendously large speed? Okay, now if this is true, say this is 0.75, then we are not measuring this L. Really what we're doing is we're measuring the shortened length of that. Okay, right? As soon as I start putting this velocity here, I have to say it's measuring the shortened length of the contracted length of the rocket. If that arrow's not there, we're measuring the proper length. How do you calculate that? You'd say, well, I'm going to calculate L prime by being L of the rocket divided by gamma. This gamma, remember, is the square root of 1 minus v squared on the bottom here. So I have to take my 0.75 and pop that in here and get that the rocket length is contracted by that amount. I think I wrote that down here, and it turns out to be somewhere in the range of about 87 and a bit meters. Call it 88 meters. Okay. So we here on Earth measure a contracted length for that rocket ship, because the rocket ship is moving past us. Now, likewise in the rocket ship, if you're measuring the proper length of the rocket ship and you're saying, yeah, this is 130 meters, what are you seeing Earth doing? Earth is flattened, right? It's been taken from a spherical shape into kind of like a football standing on its end type of thing. A football meaning an American football. If you stand it on its end, that's the kind of shape that Earth would have as it moves past the rocket ship the other way from the rocket ship perspective. I wanted to give a little bit of historical perspective to the length contraction argument. It is also known as Lorentz contraction. And Lorentz, if you have studied any physics history before, Lorentz was someone, Hendrik H.A. Lorentz was a forerunner of Einstein's. So by the time Einstein came up with special relativity, I think Lorentz was, so Einstein was in his 20s, in his mid-20s when he did this. Lorentz was already past 50, I think, was somewhere like that by the time he did that. But nonetheless, it's known as Lorentz contraction because Lorentz actually came up with it first. However, all he came up with was this. Why did he come up with that? The reason he came up with that was because, a little bit of history here, everything that's a wave that we are aware of travels through something. There is a medium that carries that wave. Sound is carried by air. the water is carrying the water waves. Okay, so the question is, since we know light is a wave, what's carrying the light waves? There must be some medium that's carrying the light waves. And they came up with this thing called ether. In other words, Earth is moving through ether because light waves are traveling from the sun to Earth. Therefore, space must be suffused with this ether that carries the light waves for us. Okay? So, if that's the case, then Earth's perspective is Earth is moving relative to that ether as it goes through space. If that's the case, then we should be able to detect Earth's motion through the ether. And they did that with what's called an interferometer. In other words, an interferometer is a fairly straightforward device invented by Michelson. It shoots light this way and comes back. It shoots light this way and comes back. So if light is propagating through the ether, it takes different travel times if it goes at right angles like this. The problem was that Michelson never found a difference, because what would happen, as you would know, is light going back this way, hitting off a mirror coming back, will interfere. But Michelson never measured a difference in the interference pattern, no matter if he rotated the apparatus, waited till summer, spring, winter, as we're circling around the sun, right? He never measured a difference in the interference pattern. So Lorentz came along and said, well, one way for that to be true is if one of these branches is shortened along the direction of travel with respect to the other one. And that's how this became known as Lorentz contraction, because Lorentz actually came up with this, but had no physical reason for saying why this should happen. He just said, well, it would make sense that the light never changed its interference pattern as long as this direction was slightly shorter than we thought it was, or light thinks it's shorter than we think it is. So he came up with that idea, and it wasn't until Einstein put it into perspective of actually this is a condition of two things moving relative to one another, that the contraction happens, and it's also messing up the time measurements. So Einstein was really the one who put the whole thing into perspective. However, it is often known as Lorentz contraction because of that story and Lorentz's contribution. Anyways, I see that we are just about out of time for today. So I will leave it here, and we'll go through, do a couple of more examples. I want to put together a few things left over tomorrow, which is why we postponed the homework until Tuesday of next week, because being due Thursday is a little bit crunched. So let's stay on target with Tuesday of next week. I'll finish up the relativity stuff on Wednesday of this week, which should give you hopefully enough time to circle back and finish that off for next week. Okay, so at that point, I think I'll say this is the end of today, and I will bid you happy rest of your day. And if you book an appointment at the dentist at 3 o'clock, make sure that you are not traveling relativistically prior to that, otherwise you will not arrive on time. So just to let you know. Maybe you don't want to arrive on time for the dentist, and I understand that too. Alrighty, so I will see you next time. Until then, folks.